Good evening, peeps. So now what are we doing? I'll tell you what we're doing. We're doing the practical. It's good to talk the talk, but it's good to walk the walk, and this is it, showing why the light from the sun is absolute. That's Mercury, Venus, Earth, Mars. For this exercise, that thing that's shining is a 3mm bulb, but we're going to call it 5. Okay? Three millimeters. And of course, for scale, for depth, we've got Jupiter. So how would Jupiter? Bong. Bong. Right, so it's silly. So what we have are 5 planets and the sun, right? These planets are to scale. What I mean to scale, we've got the sun that has a diameter of 3 millimeters, all right? Doesn't look possible, does it? But it is. I'm going to call it 5 just to keep the working out a bit tidier. There we go. It's a little tiny thing in the middle, right? See it? It's like a little cat's eye, isn't it? That's tiny. We're talking, 3 mil. Right, I'm going to call it 5 for this exercise, okay? Now, what I've done, we've got a we're going to call it a 5mm bulb. So with a 5mm bulb, I want to keep everything to scale, okay? I want everything to scale all the way down to Jupiter. Now, Mercury at 69 million kilometers away, if we divide the 69 million kilometers by the sun's diameter, we get 49 sun diameters. We then multiply that sun diameter by the 5mm bulb, and we get 25.4 centimeters. So that is the distance. Now, don't forget, Mercury, all of these planets are tiny, right? We're talking in the micrometers. So Earth's diameter there, that top one, because I did 3 mil, right? So we did 3 mil times 108 is 32.4 centimeters for the distance, and we divide the sun by 109 and we get 0.0275 millimeters. Now that's 27.5, or yep, it is 27.5 micrometers. Okay, it's tiny. And then we have, it's 0.2, it's 27 micrometers, sorry, 27 micrometers. There are 1,000 micrometers in a millimeter, okay? There are 1,000 micrometers in a millimeter. That Mercury would be 27 from 1,000. Tiny, right? So then we've got Earth. So I did the Earth at 5 millimeters. This is just for depth, just to compare it with something. We multiply the 5 millimeters by 108 and we get 54 centimeters. That's the distance between the 3mm bulb and the planet Earth. But Earth would now be 0.0459 of a millimeter. So that's just under a 20th of a millimeter, right? And then at 1 centimeter, if we had a sun diameter of 1 centimeter times 108, it would be 1.08 meters to Earth. And we divide it by 109 because that's how many Earth diameters are in the sun. And it would be 0.09 of a millimeter, right? So that's just under a 1/10. Right? And then it just keeps going up. to get to 5 centimeters. 108 multiplied by 5, that's 5.4 meters distance. Divide the sun diameter of 5 centimeters by 109, and we get 0.458 of a millimeter. That's just under half of a millimeter. So with a 5 centimeter sun, diameter of 5 centimeter sun, if you want to have a play, 5 centimeters in diameter, you get the distance between you or us and the sun is 5.4 meters. And then your Earth would have a diameter of just under half a millimeter. Right? And you can have a play and you can see, go, whoa, that's, yeah, you get the distances. So I did, they are right, what we did to Earth, right? 150 billion kilometers between the sun and Earth. We divide 150 million by the sun's diameter to get the amount of sun diameters, and then we multiply it by 5, the 5 millimeters, and that gives us the distance in centimeters, and it's 54 with a 5 millimeter bulb. All right, so let's not mess about. The sun is off, it's about to turn on. Let's put this here and watch this 8 minutes and 20 seconds, because obviously it has to take 8 minutes and 20 seconds because, well, there's a bug on there, look, because it's a 2-scale diagram. So you can see all the planets, so you can see what it's like as the sun slowly creep, right? So it's going to take an eternity, 3 minutes to Mercury, and then another 3 minutes 20 to Venus, and then another 2 minutes to get to Earth. So sorry about the wait, but there's nothing I can do about the speed of light radiating from the sun. Okay, here we go, folks. Let's turn this light off. Okay, find a button. There we go. What does that remind me of? Looking at this little button in the dark. Right, and oh, hang on a minute. That's not right, is it? Let's do that again. It should take 8 minutes and 20 seconds. What was that? Whoa! Bugger. What was that? Get off. Right. Did it happen again? Sorry, I got put off there. I'm crawling on my leg. And here we go. Now that can't be right. Let's have a look from the side. Very strange. It's supposed to take 8 minutes and 20 seconds because it should have kept its properties. So that's something's not right. This bulb is far too powerful, isn't it? Let's have a go again. So it should take, it's the sun, isn't it? Take 8 minutes and 20 seconds to reach Earth. Let's turn it on again. Here we go. That doesn't make sense, does it? How can that be? Right, that button's stuck. Well, there we go, boom. Right, what are we seeing here? I'll tell you what you're seeing. You're seeing what's real. What you're seeing is a 3 millimeter bulb radiate its light at light speed, okay? What we've got to scale is Mercury, Venus, Earth, Mars, and Jupiter way down there. Why are you seeing this go so fast? Well, it's really quite simple. This is the sun, right? We brought the sun down here and it kept its properties. If it kept its properties, this would radiate its light at this speed. Boom, like this. It would take 4.6 seconds for every 3 millimeter diameter. And that means to get to Mercury, it's going to take 3 minutes. To get to Venus, another 3:20. And to get to Earth, another 2 minutes, which is 8 minutes and 20. This bulb, pound for pound, would wipe the sun's arse. But it's impossible to say that. It's ridiculous, because what we would need right now, right here, is a bulb that takes 8 minutes and 20 seconds to radiate its light to here. We need a bulb that takes 4.6 seconds to radiate the light the distance of its diameter, because that is what our sun does up there. This is to scale. It doesn't matter how you paint it, what colour you paint it. This is where people start losing themselves here. If this bulb kept its properties and went up there, what happens? You've just seen what happens, right? Or are we to believe that the sun, if it kept its properties and it comes back down here, well, no, it can't, because look, we've already seen. If it kept its properties, it would go boop, 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 and then boop, 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 4.6 seconds. It's going to take 3 minutes. Look, ladies and gentlemen, nothing takes 4.6 seconds to radiate light the distance of its diameter. What do you think if we get this up to basketball size? Is it going to get less powerful? Or what if it was the size of an Olympic swimming pool, a sun the size of an Olympic swimming pool? Is it going to get less powerful then? Okay, what if we've got a sun the size of the Tampa Bay Buccaneers Stadium? Is it going to get weaker and slower then? Light, not slower, because light is a constant. It is a constant. It's absolute though, not 299,792. Tampa Bay Bucks sports ground, the football stadium. A sun that big, is it going to get slowed down? Is the light all of a sudden going to take 4.67 seconds to radiate light its diameter? What if the sun is the size of an aircraft carrier, but round? That's bigger than the Tampa Bay. Oh, maybe not. What if it were the size of Cuba? What if the sun were the size of Cuba? Do we think it's going to slow down its light? When does it start to happen? This 4.6 seconds for each of its radiators. If Cuba was the moon, the sun, and just squished so it's round, is it ever going to take 4.6 seconds for that sun to radiate its light the distance of its diameter? No. How about the moon? Next size up. We've got the moon. Now, is the moon ever going to take 4.6 seconds? Because it's that we're talking big now, right? I know. What about Earth? What about if we had another Earth as the sun? Can you see Earth, if it was a star, taking 4.6 seconds to radiate light the distance of its diameter? No. So why do you expect the sun to slow down all of a sudden with its light? People, it's staring you in the face. This proves it. The light from the sun is absolute, right? And this is exactly how it would light up the solar system. And when I say you wouldn't see a difference if you had somebody on Mercury and somebody way back there on Pluto, with a click when you see the light, they would both click together. That's how fast light is. See it as it lights up. Don't forget, this is to scale. That's what would happen if you were behind the sun and it lit. And this is what would happen if the sun was on and it suddenly turned off. There's no 8 minutes and 20 seconds for people to... Oh, it's just pathetic. It's ridiculous. Light is absolute. No source, no light. Oh, but it's small. Hey, this sun is to scale. You think there is something with a diameter, any kind of diameter, that takes 4.6 seconds to radiate light the distance of its diameter? You do, the sun, then you have no common sense. Keep fighting it. Keep fighting this. The actual evidence that proves that the light from the sun is absolute. It's a bulb. Yeah, I know. Kicks the sun's arse though, pound for pound, isn't it? Because the sun would take 4.6 seconds. That's the bit you're missing. That's the ridiculous bit. This is perfectly normal. What isn't normal is to think that a star somehow loses power and takes time to radiate its light. It's insane. Things don't get less powerful and slower as they get bigger. They get more powerful. Crying out loud. God, they have you people thinking. Talk about illogical. Anyway, you won't get a better show than that for the speed of light radiating from the sun. Later, peeps. I am writing again, by the way, so that'll probably be out tomorrow. Yeah. All right. Laters.